Delta Lake is an optimized Spark table that brings data reliability and performance optimization to the scale. It makes your data lake faster, more reliable, and accelerates the pace of innovation. Welcome to Ask Trailblazers. I'm Upsert, and in this video, I'm going to talk in detail about Delta Lake and how you can use it in a Spark pool of Azure Synapse Analytics. Delta Lake is an open source storage layer. It's a sub-project of the Linux Foundation. It sits in Azure Data Lake Store when you are using it within a Spark pool of Azure Synapse Analytics. It provides several advantages. For example, it provides ACID properties of transactions, that is, atomicity, consistency, isolation, and durability of the table data. And it does by doing following. Number one, it keeps track of ordered record of every transaction since Delta Lake table creation in the transaction log, and checks it prior to every read and write operation to allow atomic transactions. Number two, its serializable snapshot isolation level ensures that reader never see inconsistent data, and they can continue to read the data while writers are writing data concurrently. This means literally having no impact to read the consistent data even when the data load in the table is in progress. And number three, it employs all or nothing ACID transaction approach to prevent data corruption from failed write operations. With its scalable metadata handling, it leverages a Spark distributed processing power to handle the metadata for petabyte scale tables with billions of files at ease. It provides unification of streaming and batch processing. With that, a table in Delta Lake is a batch table as well as a streaming source and sink. A streaming ingests data in real time, batch load processes historical data, interactive queries query data interactively, all at the same time. And it all just work out of the box. Schema enforcement and evaluation feature automatically handles schema variations to prevent insertion of bad records during data ingestion. With time travel, every operation is automatically versioned. That means data versioning enables rollback in case required, full historical audit trails, and reproducible machine learning experiments. For upserts and delete operations, it supports merge, update, and delete operation to enable complex use cases like change data capture, slowly changing dimension operation, streaming upsert, so and so forth. Now is the time to get started with Delta Lake. Here we are in Synapse Studio. If you are new to Synapse, you can refer to my introductory video on Synapse Analytics. On this page, on this home page of Azure Synapse Studio, let's click on Manage. Then let's click on Apache Spark Pool. This is a page where you'll see all the Spark pool that you have created in this workspace of Azure Synapse Analytics. If you are new to a Spark pool, you can refer my previous video which talks about the Spark pool in detail and get you started on a Spark pool. Before we get into details of executing the code with Delta Lake, let's look at the Spark pool that we have so far. At this time, I can create new Spark pool against which I can start executing my Delta Lake queries, or I can use any of the existing Spark pool that I have already created to execute my code. And I'm going to do that with the existing Spark pool that I have already created. So this is my Spark pool that I have already created. And before we get into details of executing the codes, let me show you some configuration of this Spark pool. If you click on the hyperlink of this Spark pool, it opens up a page where you can look at the configuration for this Spark pool. Expand this configuration section, and what you see over here is this pool is based on Apache Spark version 3.1, right? And this distribution includes Delta Lake version 1.0, which is the latest version at this point in time. right? So this is the configuration that I've used for Spark Pool. Apart from that, let me close this. If you click on this icon that you see over here for a skill setting, click on this icon, and what you notice over here is this option to dynamically allocate executors. So this is a recently introduced feature with the Spark Pool, and what we can do with this feature is, like, when we are going to submit the job, the submission creates a Spark session for the execution of that job. Underlying there is a Spark cluster. So how many executors are going to be part of that Spark cluster that's going to be created, right? There is a default setting based on that the Spark cluster gets created. You can change those default configuration and make it the specific number of executors, or you can enable dynamic allocation of executor based on the workload that you are trying to execute. So if I enable this feature, it's going to ask me what's the minimum number of executor that I want to have for this Spark cluster when I'm executing the query against this Spark pool, and what's the maximum number of executor that I'm going to have for this Spark session, right? And this is something, a slider that I can slide, and in this case, because my Spark pool has 5 nodes, so I can go up to 5 nodes maximum as number of executors, and on the left side I can drag it to 1 or 2 or 3 based on the range that we want to define. So with this configuration, when I'm going to start executing the job against this Spark pool, this underlying Spark cluster that gets created, that will get created with 2 default executors, and as the workload demands, the number of executors will be added up to 5 in this cluster. So this is the new configuration setting that has been kind of released recently, and you can leverage it for your workload. Let me cancel this and go back to the develop section. If you click on this, click on notebook, I have this one notebook that I have already created for us to go through and look at the demonstration of how Delta Lake works. You can find the link of this notebook to download it from GitHub along with the deck that we used earlier for the introduction of Delta Lake, and you can click on this notebook on a section in the Azure Synapse Studio, and you'll see there is an option to import. So you can import the notebook that I have provided you to kind of import it in your workspace and play around with all the codes that I'm going to walk you through at part of this demo. Now, first thing first, if you can see, this is the notebook default Delta Lake demo part 1, and this notebook is attached to the Spark pool that I just showed you earlier with the configuration that we have. And the default language for this notebook is PySpark in this case, right? What we are going to do first is going to execute this command to see what's the default configuration for the number of executor instance, cores and memory, right? So let me start executing this command. This command might take few seconds to a minute or two based on when you had your cluster created. While this executing, let me click on this outline, and what you see here is a section where we have a table of contents. So this table of content is basically the different section in the notebook different section that we have in this notebook, right? So the very first section that we have here is for notebook configuration. Then we have another section in this notebook for preparing the data to kind of go through this demonstration. The next one is converting existing Parquet file to Delta format, and likewise there are multiple sections over here. You can click on any of these sections to directly jump onto that part and start executing the code as part of that section. With that, let's go back to the configuration again, notebook configuration again, and wait for this command to get executed. We can close this outline window for now. We can minimize or collapse this notebook section for now so that we have more space for us to look at the code, actual code getting executed. The command has completed successfully, and what we see over here is the default configuration related to the executor for this Spark pool. So we have only one instance, and then we have 4 core in that instance, and there are like 48 gigs of memory is there on that instance. Because we are going to deal with like larger data set, let's have more number of executors to run it parallelly across distributed node, right? And to do that, we can use percentage configure magic command to change the configuration for the executors. And what we are going to do in this case is to specify the number of executors as 4, and executor cores are going to be 4, in which case like each of the executor will have 4 cores, in total 16 cores in the cluster, and each of those executor will have 28 gigs of memory. Because we are saying -f, so this configuration will be applied and session will be reset. So let me start executing this code. This code will take couple of seconds because we are resetting the sessions. Now, as you can see, the command has executed successfully, and we can validate if these changes were applied or not by executing this set of command where we are saying spark.conf.get. This is the API that we are calling, and this is the configuration key that we are passing. It's going to return us the number of instances that we have in this session or in underlying cluster, Spark cluster, and the number of cores in each of those instances, and then the amount of memory that each of those instances has. Right, so we have changed the configuration to make it 4 executors in the underlying Spark cluster. Like I said earlier during the Spark configuration demo, this is a new feature which Spark pool team has introduced to dynamically allocate the number of executors that you want to be part of your Spark cluster. When you're setting this configuration at a Spark pool level, every time an instance is getting created, that configuration will get applied to all the Spark session that's getting created or underlying cluster getting created. However, if you want to keep it at the notebook level, you can do it with the percentage and configure command again. This is the magic command that we used earlier. You can use that again to kind of change that configuration. And in this case, you have to say dynamic allocation and enable is equal to true, right? So this is the key that we have. Spark.dynamic allocation.enable, and we have to set it to true, and then we have to specify the minimum number of executors that we want to be allocated when the execution starts, and the maximum number of executors that it can scale up to when the workload has more and more work to do, right? So this is the configuration that you can specify at the notebook level, right? So this dynamic allocation of executor is possible both at the Spark pool level as well as on the notebook level. You can do that. I'm not going to change it at this point in time. I would recommend to change this to dynamic when you have a long running job. In our case, our jobs are very short-lived jobs, so the scaling would not help in this case. So we have a fixed number of executors already created for that purpose. Now let's go to the next section, and what I'm going to do now is, like, it's very likely if we have been using Apache Spark for some time and the default storage format is Parquet, it's very likely that you have data already in Parquet format, and when you want to transition to Delta Lake, the first question comes is how we can convert that Parquet file to Delta Lake table format, right? And that is what I'm going to demonstrate to you next. And to do that, what I'm going to do is I'm going to take New York Yellow Taxi data from Open Data Set for 2 months. This is going to be January 2010 and February 2010. This is a start date and end date that I have specified over here, and create a data frame. And before I can write that data, I want to make sure it doesn't contain any duplicates, right? And for that, I have called this drop_duplicates API, or function to drop all the duplicates in the data. And I'm going to repartition this data into 32 partitions. By default, shuffle partition has a value of 200. So it means like every time when there is a shuffle involved, 200 partitions will get created. And because in this case the data volume is not that huge, even though like 200 partitions are getting created and 200 files are getting created on the storage, all those files are very small in size, right? And as you know, big data systems are designed for processing a small number of large files, right? If you have a large number of small files, you might see a hit on your performance, right? So we have to optimize it by keeping a small number of large files. So that's the reason I'm kind of keeping it 32 for now, right? So I'm repartitioning it over here and creating this data frame. So let me execute this command. The command has executed successfully, and we have this data frame with all the definition that we defined earlier. Now what we are going to do is write this data frame as Parquet file into the data lake store. In this case, it's going to be default data lake store for this Synapse Studio workspace, right? And I'm going to do it in two ways. First, I'm going to write this data as Parquet file without specifying any partition. So this is going to be non-partition Parquet files, and the same data I'm writing it as a partition files, and in this case I'm partitioning it in on year and month. So a year and month are two columns in the data. I'm using that to partition the data, and I'm writing that data into the same default data lake storage, but in a different form, different folder. So let me execute this command. While this command is executing, you can also kind of expand this section, and you will see that you'll see all the jobs getting created by executing the commands in this cell, right? So the very first job is running at this point in time, and you can look at the summary of what's going on, right? You can click on view and monitoring, which will take you to monitor page of Azure Synapse Studio, and you can get more details about what's going on behind the scene when this job is getting executed. Or you can click on open a Spark UI. That's a standard Spark UI where you can look at more details about the execution of this job that's going and what's going behind. I'll talk about monitoring in detail in my next video, but yeah, these are the options that you have available to look at what's going on behind the scene when a job is getting executed. So in this case, as you can see, I have two write operation basically, and that triggers two jobs to be executed. My very first job is currently running, and once this completes, there will be another job to write another set of data, and here it is. You can see job number 3, and this is kind of writing the data from the second write operation that we have over here, and it's going to be partitioned by year and month. The command has executed successfully, and as you can see, this write is an action operation, and each of this write has initiated a job, and both of these jobs have completed successfully. We can go back and look at the data lake store where this data has been written. So as you can see, the data is in the default data lake store for this Synapse workspace, and within this data folder there is a Delta demo and then Parquet TBL for the first write operation, and for the second one it's going to be partition Parquet TBL, right? And this data, the second data, is going to be partition. So to look at the data that we have on the data lake store, we can use Azure Storage Explorer. This is a free utility from Microsoft which you can use to kind of manage and work with the content from your data lake storage account. As in this case, as you can see, I have connected to Azure Blazers. That's my data lake storage account, and this is the default for my workspace that I have. Within this data lake storage account, Trailblazers is the container. And if we look at this container, let me go back here in the container, and you'll see there are multiple folders over here which I have created for my purpose. And the one folder that I'm interested right now is the data folder, because this is a place where we created those files, Parquet file, and within that we have this Delta demo folder. If we click on this, you'll see there are two folders getting created, one from the first write operation and the second one from the second write operation. The first write operation is where we kind of wrote the data as is without specifying any partition. However, when we wrote the data, we said the data should be repartitioned with 32 partitions, which translates to 32 files getting created on the data lake storage account. And if you look at the number of files over here, this is 33, and if we exclude this success file, this indicates 32 data files created, Parquet data files getting created for the first table or first write operation. Now if we go to the Delta demo folder again, and if we can look at the second folder, because this write was based on partition that we have created, and partition is defined as year and month, and in our case the data is for 2010 and for January and February. So this is what you see, year is equal to 2010, and if you can drill down into that one, you'll see month is 1 and month is 2. If you click on any of this, you'll see there are 32 files getting created because of the repartition of the data frame that we did earlier, and this is 32 for month 1, and likewise 32 for month 2, right? So this is how the data gets written, and you can validate by going to the data lake storage account. You can use Azure Storage Explorer, or you can use Azure Portal to look at the content that has been written by this process. Now what we want to do in this case is, assuming that you are coming from Apache Spark background and you have tons of Parquet file already created, and you want to convert that Parquet file to Delta Lake format so that you can take the advantage of what Delta Lake provides. And one of the simplest way is to kind of read the Parquet file and write that data as Delta file, which might be good for a smaller data set, but will be very time consuming if the data volume is very huge. So reading the data and writing it back as a Delta table is going to be very time consuming. And knowing that Delta Lake also has the underlying file storage format as Parquet, but it has additional metadata. What Delta Lake community has done is basically created a command or an API which you can leverage to convert this Parquet file efficiently from Parquet to Delta format. So when you use those API or the command that I'm going to show, instead of reading the data and writing the data in its entirety, it just creates some metadata around the Parquet file that's already created, right? And it does by looking at the number of files that this folder has and all those details, and it creates the transaction log for this data, or basically the metadata for this data. So at this point of time, if you look at this folder, it just has the all the files that was created as part of the data files. It doesn't have any transaction log at this point in time because it's a Parquet table or Parquet set of data. So let's go back again to our Synapse Studio, and what I'm going to do is basically I'm going to convert this Parquet files to Delta Lake format. And to do that, I need to first import this library and import the Delta table class, and this class has a method called convert to Delta, right? And this takes the location where we have this Parquet file as an input and converts that to Delta Lake format. And basically what it does is it just creates some metadata. It does not read and write the data, and that way it saves the amount of time that it has to run the process, right? So this very first command is going to run for set of Parquet file which are not yet partitioned, right? So we just specify the location of the Parquet file, and it's going to kind of create the metadata for those set of Parquet file. Let me start executing. While it's executing, I'll explain you the second part. If you look at the second convert to Delta API call, in this case I'm specifying the location of my Parquet file, which is kind of partitioned, and the next parameter for this API call is the information about the column and the type of the column on which this data or the Parquet file has been kind of partitioned. So in our case, it's been partitioned on year and month, and this both are int type. I have specified over here, and it's going to kind of look at the partition structure of the Parquet file and create the metadata based on that structure. Now this command has executed successfully, and as I was saying earlier, irrespective of how big that data is, the amount of time it's going to kind of create the metadata will not be that much, considering the number of files are not that huge, and the reason is because it's not reading the data, it's just creating the metadata for all the Parquet file that's already available. And we can go back to a Storage Explorer again, and we can validate that. So let's go back here, Delta demo folder, and if we click on Parquet table again, at this time you'll see there is a folder created, and it's called _delta_log, and this is in addition to all the files that we had earlier. So there was no change in the data file as such, but a log file has been created, and this log file has a JSON file which is a transaction log of what this set of data contains, right? So what all files are there and all those things. So this JSON file will contain all those information. Likewise, if you go to the other folder that we have for the partition Parquet file, click on this, and if you see here, we have the same folder getting created over here, and we have the same JSON file created which contains the transaction log for all the data that we have. We can click on this file, and we can look at the details, what it contains. I'll keep the detailed discussion in the second part of this video, but in the first part of the video, let me kind of introduce you to what it contains, and we'll get into details of each of the section in the second part of the video. So here we have the JSON file, which is kind of transaction log, and if we can look at this detail, you see this file was created from the operation called convert, because this is what we executed to convert it from Parquet to Delta format, and this data is partitioned by year and month, and there are 64 files into this table, and this 64 is coming from the fact that we have two partition, and each of the partition contains 32 files, and details about all those files are available here in this section. If you can see, add item, add path, and then we have like 32 for partition 1. If we go from here to here, it's all partition 1. This is what you can see, and the rest 32 are for partition 2, right? So this is the metadata that's created when we convert it from Parquet to Delta format. And the same JSON file, if you open for the other table that we created, it will have the similar information, but that will have only for 32 files because we do not have any partitions over there. Now let's go back to Synapse Studio, and what we did here with this command is basically we used PySpark API to convert Parquet file to Delta file. If you are a SQL developer and you are looking for a similar capability but using a Spark SQL instead of PySpark API, there is a similar command or equivalent command to do that on a Spark SQL side, and this is called convert to Delta, and then we say Parquet dot location of the file that we are going to convert. right? So this is the Spark SQL command, and because this notebook has a default language as PySpark over here that you see, and we want to execute this cell as Spark SQL, we have to specify a magic command percentage SQL to indicate that the command or the script in this cell needs to be executed at SQL command or a Spark SQL command, right? So this is one command to convert a set of Parquet file which is not yet partitioned. The next one is about converting a set of Parquet file which is already partitioned. So we say convert to delta and Parquet dot the location where we have those Parquet file partition by, and then we specify the partitioning information. So this command has equivalent effect as the previous command. I'm not going to execute this, but this is another way to achieve the same thing what we did earlier. Now the next thing is, say for example we are working on some new development and we have a set of data frame that we are dealing with. We can use the write API and use the format as delta to write the data of the data frame as delta in first place itself. We don't have to write it to Parquet and then convert it to delta. We can simply write it as a delta, and while it's writing the data will be stored as a Parquet file, and the transaction log will be created and stored into underscore delta underscore log folder, right? And the process is very similar to the one that we had earlier. So the only difference here is instead of saying Parquet, we are saying delta, and rest other command to kind of to write this data will remain same as the earlier one when we wrote it as a Parquet file. So this is one way to kind of write the data as Parquet. In case if you want to kind of write that data of the data frame and create it as a managed table, you can use this command. So you can say data frame dot write and format is equal to delta. Then mode is equal to overwrite if you want to overwrite, and then you use the save as table as API call, and then you specify the name of the table that you want to create as a managed table. So this data frame, when it's writing the data, it's going to write the data as a managed table, and the table name will be this one, the one that we have specified over here. Likewise, if you want to create a managed partition table from the data of this data frame, this is the command to execute. So in this case, we are saying partition by, and it's going to be partition on year and month, and saving it as save as table, and we are specifying the name of the database table that we are going to create while saving the data, right? So there are two ways. Once we have the data frame, we can create a managed table by writing the data of that data frame, or we can write that data as delta and create a table, external table on top of that delta files created over there, right? So let me go ahead and execute this command. So this command executed successfully. To validate if these files have been created as a delta table or data files, we can go to Storage Explorer one more time, and we can go to delta demo. This is the place where we have created those files, and if we can click on a delta taxi trips folder, you'll see that there are 32 files for all the data that we have that was part of the data frame, and this has been created as a Parquet file. It's very similar to the way we did it earlier. The only difference that you see here is there is a delta log folder, and this contains the JSON file, which is the transaction log of the operation that we perform on this delta table, right? Likewise, if we go back to delta demo folder again and go to delta partition taxi trip, you'll see that delta log folder again over here, and the same JSON file has been created over here for the metadata that this data set contains, right? So this is how the delta log folder gets created, and the transaction logs are getting created as part of the operation that we are executing against this delta lake table. So far we have written the data that we had as part of my data frame, and we have written that as a delta file. What we can do next is basically we can create external table pointing to those delta file location. And to do that, what we do is we simply call create table if not exists, just to make sure creating the table if it is not existing, and then we are specifying the name of the table. So in this case it's going to be delta demo, that's the name of the database, dot table name and delta taxi trips, and we are saying using delta. This indicates the underlying data format for the data is delta lake format, right? So we are saying using delta over here, and then we are specifying the location where this data sits, right? So in this case we wrote this data into data, delta demo and delta taxi trips. Likewise, for the second table we are going to name it as a delta partition taxi trip, and we are again going to say using delta because underlying file format is delta. And then in this case it's going to be data, delta demo and delta partition taxi trip, right? So let me execute this command, and while it's executing we can see that this is not the only way to kind of execute this command. So what we have done in this case is basically we used PySpark API to create the database and the tables within that database, but if you want to use Spark SQL, you can pretty much do the same thing using a Spark SQL. So in this case we are saying create table if not exist, and we are specifying the name of the table, again very similar to the previous one, and using delta, and we are specifying the name of location where the data exists, right? So either way is fine. You can execute either this command or this command. In both the cases the outcome is going to be same. So once these tables are getting created, we can go back and look at the details of this table. So we have this describe command, and we can specify the name of the table, and there is a detail parameter for this described command which gives us the detailed information. So let me execute this command, and while it's executing, let's go to the details of the outcome that we have got so far. For the very first table, you see that these are the columns that is in part of that delta table, and this is the delta data type for each of those columns. And if we can scroll down, it gives another row where we have the further details about the delta table. So format in this case is going to be delta, and name of the table is going to be, this is the name that we have specified over here, and this is the location where the data sits, right? So this is the location that we have for the data lake store, and there are a couple of other information in this detail, right? The very first table was non-partition table, so we do not have any information for partition column over here. But if we can scroll down and look at the details for the second table that we created, which was a partition table, you'll see that we have the partition on year and month, and the number of files which exist as part of this table is 64 at this point of time, and this is the total number of bytes of data in that table, right? So this is the kind of information you can gather about delta table using describe table command or describe detailed table command. We have the table created. Now the next step is start merging some data into that table, right? To do that, let's first quickly look at the data that we have. So if we execute this command and look at the data that's going to be returned by this command, is basically doing aggregation on year and month, and then we are taking the count of rows that we have in each of this month, right? So this is the total number of records in each of those months. So this is for January and February. So we have data for say two months of year 2010. And what I'm going to do is basically I'm going to take an incremental data and going to simulate a scenario where we have a table already created with lots of data into it, and there are incremental records coming in, and we want to merge that incremental data into the table that we have already existing, right? So we created those existing table already, and I'm going to create another data frame with incremental data that's coming in, right? And in this case, I'm going to say the data is between February 1st till end of March. So basically it's going to bring 1 month of data, which is of February. It's going to be kind of the data which is already there in my target table. So those data will get updated, and the data for March is not there in the target table. So those data will get inserted if we are trying to run Upsert or merge command against the target table. And again, the way we did earlier, right? So we are dropping the duplicates from the data frame. We have some duplicate data coming in, so we are removing those duplicates from the data frame and repartitioning to 32 to create 32 partition and underlying files. And then we are going to create a temporary view from this incremental data frame. So we have this incremental data frame which is clean, and we are calling create or replace temp view, and we are going to name it as a delta incremental taxi trips, right? So with that, let me go ahead and execute this command. And while it's executing, let me go to the next command that we have. So the next command is where we have this merge statement. So merge is the command that you use to upsert the data into your target table. So what we are doing with the merge here is, with merge, we are saying into the target table. So this is my target table. This is my existing main table in which I want to merge the data into. And then with using, I'm specifying the incremental table that has the incremental data coming in. So in this case, I'm kind of aliasing this table as a source and target table as target. And then with on, I'm kind of specifying the column on which I will be kind of identifying the unique row and doing the comparison from the both sides. In this case, because there is no unique case, I had to use multiple columns to uniquely kind of identify one row and compare it between source and target. But in your case, you'll have the unique key, and I would highly recommend to use the unique key of one column or like couple of columns, not this many columns. If you have this many columns, the performance is going to be slow. I had no choice because there was no unique key in this case, so I had to take multiple columns to make it a large composite key. But your goal should be to minimize the number of columns that you are kind of doing the comparison against, to minimize the overhead in doing this comparison and executing this merge statement faster. So this is with the on clause, we specify the condition on which the row from the two side will be kind of joined and compared against. The next one is the very important one, right? So think of a scenario where you have a target table and you have yearly and then monthly partition on that target table, and the target table contains the data for say 10 years. So in this case, you have like 120 plus partitions already in your target table. And when you're going to run the merge statement without kind of specifying anything, it's going to take the data for all 20 partitions or all the partition on that table, and then kind of going to do the comparison and going to update the record when there is a match, if not going to insert the record for the new record. So that is going to be very time consuming. You can apply partition filter over here to prune the partition from the merge execution itself, right? So in this case, what I'm saying here is, I know that my data is for year 2010. So even though my target table might contain data for say 2008, 2009, or maybe 2007, but because I'm applying a filter on my target table and saying year is equal to 2010 and month is equal to February and March, it's going to only consider those two partitions from year 2010. So that way it's eliminating all the other partition when it's executing the merge statement. So given the number of partitions that you have, you'll see significant change in the performance by this partition pruning technique. So keep that in mind whenever you're using merge statement. Try to see how you can prune the partition from your target table to only kind of focus on the partition which has the data getting updated or getting merged. So this is the second part of on clause. The next part is when matched. When the data matches, what we have to do. So we, in this case, we are saying when the data match, or basically the unique key from the both side match, then update the data into target location. I'm saying target dot location ID, target dot store and forward flag, target dot fair amount with the data which is coming from the source. In this case, if you see source dot fair amount, source dot store and forward flag, source dot location ID. So when there is a match, it means the record has already come into my final table or target table, but there is an incremental data coming in, so I have to go back and update. So when there is a match, update the existing data with the new incoming data. And when there is no match found, then insert the data as if it's a new data. So let me execute this command. My previous command has executed successfully. Let me execute this command. At this time, the merge command has executed successfully. Now if we go back and execute this same command we executed earlier, we'll see that this time the table has data not only for January and February, but it has the data for March as well. And here it goes, right? So as you can see, we had data for January, February, and now we have the data for March. So March data has been inserted as if it was the new record coming in, and February data was updated. I just simulated bringing the same data for February, but in your case, when the data for the previous period is coming in, most likely those are change record and they will have a different impact on your data, right? In this case, the previous data for February and the newer data for February was same, but I just wanted to show you that you can update the existing record, and when you do that, it will be the new record which will kind of which will be written over to the existing record or the old record, right? So that's possible with Delta Lake, right? So this is what we see over here. Now if we kind of if we prefer Spark SQL, we can use merge statement to kind of upsert the data into our destination or target Delta table. But if you are a Python developer, or if you're looking for a PySpark API, you can again use Delta table class and call the merge API and achieve the same functionality using the Python API as well. I'm not going to execute this command, but yeah, know that there is a possibility in case if you are interested in executing the same command or achieving the same outcome with Python API instead of Spark SQL command. Now is the time to look at time travel or history of changes which gets kind of automatically being versioned by Delta Lake table. So let's say we have data for January, February and March, and accidentally someone deletes the data for January, and let me do that by executing this command. So if I execute delete from table name where year is equal to 2010 and month is equal to 1, it's going to execute and delete all the data, and you can see that the command has executed successfully. And at this time, if I go back and execute the same query which I executed earlier to see the data for the year, month and the count of record in each of those months, I'll see only the data for February and March. I'll not see data for January because I deleted that data and that's no longer active record, right? So this is what I was expecting. I see data for February, I see data for March, but there is no data for January. Now, because I said this maintains the history of all the changes, or all the changes are being kind of versioned over here. And if you want to look at what are those version for a given table or the Delta files that's sitting on the Delta Lake location, we can execute this command, describe history and Delta and the location where we have this Delta Delta Lake files. So if I execute this, you'll see that all the version that has gone through after making all the changes into this table is being captured over here, and this is what you'll see. So this is version 0, version 1 and version 2. Version 0 is when we kind of wrote the data as a data frame to delta file, and that is what you will see over here when you expand it the operation parameter. So if you see here, we overwrite the data and partition the data by year and month, right? And version 1 is basically when we kind of ran the merge statement to merge the data. So in this case, if you see here, it's telling us the predicate on which we kind of compare the two row against, and what we did when there was a merge match, and what we did when there was no match, right? So this is the second command that we executed against that delta table. And the third command that we executed was the delete command that we kind of executed to delete the data from that table, right? So this is all the version being stored and maintained for the Delta Lake table, and this is all automatic. It comes all out of box, right? So this is the delete statement, the most recent one, then the merge statement, and this is the write statement. Now, like other cases where you can use a Spark SQL to kind of work with Delta Lake table, you can again, if you want to look at the history of all the changes that has been applied to a Delta Lake table, you can use Python API, and in this case again, you can use Delta table class and call the history API to get the history of all the changes, and you'll see the similar record coming up over here for this execution as well. So let me execute this, and you'll see similar record coming up what we saw earlier when we executed described history and delta table. The next part is where we want to kind of go back into history and query the data as if it was active at that point in time, right? So what we see over here is we deleted the data, right? And that data, that operation created version 2. So when we kind of, so most recent version at this point of time is version 2. If I go ahead and select from this table, it's going to give me the most recent version, which is 2, and that will have that will not have any data which we deleted, right? Now suppose we want to go back into history and we want to query the data before the delete was kind of executed, and that is when the version was 1, right? So if we go ahead and kind of read the data, we say spark.read.format, in this case delta, and option is equal to version of. So this is the keyword that we have to use, and we have to specify the version which we want to read from this delta table, and this is the location which has the delta file. So if we go ahead and execute this command, it's going to give us all the rows or kind of all the data before delete was executed or until version 1 was created, right? So in this case, as you can see, we have the data for January, February and March. So this is before the delete happened, right? So we can go back in history and query the data as if on that day it was active. So this is based on the version number that we can specify over here. We can also specify the timestamp, right? So we can also take, say for example, this was the timestamp when I created version 1, and I want to query all the data as of this version. So let me select this and go to the second command that I have in this case, and let me paste this here, and while it's executing, let me explain you. So again, this time I'm saying spark.read.format, and this is going to be delta. Option is going to be the timestamp as of, and then the timestamp that we want to query the data again. So we can either specify the version number or we can specify the timestamp, and based on that the data will be queried, right? So we specify the timestamp for version 1, and anything before or at that point in time was active will be brought into the consideration of this query execution. So at this time you can see we have the data for January, February and March. While automated versioning is a very cool feature and it helps in many of the scenario, it also has some overhead. And think of a scenario where you have data getting changed again and again over a period of time, and the system has to keep maintaining the older version of the data, right? And over a period of time you have lots of files getting created on the data lake store, and your storage cost will increase even though your active data is just a subset of total data that's stored in data lake store. But all the previous version which have been stored into data lake storage is adding up to the storage cost. So that's where you can use Vaccum command. So Vaccum command is a way to kind of remove the data which is not being referenced by delta table at this point in time, or the data which are kind of inactive at this point in time, to kind of minimize the storage cost. So given that we are today kind of querying the data for say like last 1 year, or we want to go back into history but only for last 30 days, right? So any data older than 30 days which were kind of inactive, we can get rid of it to kind of save on the storage cost, right? So that's where we can kind of run the Vaccum command to get rid of all those data. And to do that, we have to kind of execute this Vaccum command and specify the table name. And when we do not specify anything with this command, this is going to be kind of deleting all the data which are not being referenced by this delta table and older than 7 days. So that's a default retention period. So any data which is kind of older than 7 days and inactive will be kind of cleaned up through the Vaccum command. That also means that once you execute this command, you can go back into history in last 7 days only. Any data prior to 7 days has already been deleted and you cannot go back to that history. So you have to see what your business requirement is, and based on that you have to define the window in which like you will kind of keeping the older data to go back into history. At the same time you are optimizing the cost for storage. So this is Vaccum command. You are executing directly on the table. You can achieve the same functionality by specifying the path based table location. So in this case, instead of saying table name, I can specify the location where I have the delta files stored. This gives the same functionality as the previous one. The only difference here is the parameter that we are passing. In one case it's a table, and in the other case it's a location that we are specifying. Now if we want to kind of specify the retention period that we want to kind of use when we are executing this Vaccum command, we can use retain, and the numeric number is the number of hours that we want to retain that data to. So in this case, suppose we want to retain all the changes, all the history for last 30 days, and any data older than 30 days which are kind of inactive should be deleted. So in this case, I'm saying Vaccum delta and location. This is a location to look into to delete the data, anything older than 720 hours, which is 30 days. So this is how you can specify the period or the window that you want to maintain the history on, to kind of keep a balance between how long in the history you want to go back and how much you pay for the storage cost. So this is one way to do that. The other is like in other cases, like say for example, you want to kind of get rid of all those files, but before you make that decision whether we want to get rid of those files, you want to look at all those files, right? That is where this try run parameters comes in play, right? So you can execute this command, and it's going to look at all the files which are kind of candidate for deletion, right? And you can look at those files and you can see if do you really want to execute. If yes, then you can go ahead and execute any of these commands which we talked earlier. If not, then you can plan for how do you want to meet the requirement. the way we kind of execute this vacuum command in the Spark SQL, we can do the same with Python API, and in this case again we use delta table class and we call vacuum method or API on that class and specify the number of hours that we want to kind of retain the data for. Right, so this is 720 is 30 days. We want to kind of retain the data for last 30 days. If we do not specify anything here, the default value or the default retention period is 7 days in this case. The next cool feature of Delta Lake is file compaction, right? And this is very important, especially in the scenario where you have a streaming data coming in, and when you write that data, the data are getting written to files which are very small in size. So you have basically large number of small files. So that has overhead on the metadata that Spark has to maintain. So what you need to do is basically you need to coalesce all these smaller files to make it a bigger file, or basically do a file compaction to make it a bigger file. In that case, you'll have a small number of large files. So that way the metadata, the memory requirement to store the metadata will be minimized. Delta Lake has a feature to do that, and what we can do here in this case is, let's say we have the data which we merged into the destination table. So let's go back to the Storage Explorer one more time and look at the data that we merged here in this 2010 year and for month 3, right? And what you can see over here is the number of files that has been created over here is like it's 200, right? And this 200 is coming from the fact that Shuffle partition configuration for a Spark is 200. So that's a default configuration, and because we have this 200 partition, 200 files are getting created, and all these files, if you see here, they are very small in size, right? So 3 MB and less than 3 MB in size. What we want to do is we want to optimize the performance, right? So instead of 200 file, can we kind of coalesce this file or kind of compact this file into smaller number of larger files? We can do that by writing custom application or custom code, but Delta Lake has feature to do that. Let's go back to Azure Synapse Studio, and in this case what I'm doing is I'm kind of taking the path for that table that I have, and then I'm specifying the partition. In this case it's going to be 2010 and month is going to be 3, and I'm going to kind of create 16 partition. And so instead of like 200 files that I have, I want to kind of coalesce the data of these 200 files and create 16 files because I have 16 partition. So to do that, I have this command, and first part of this command is actually it's reading those files. If you look at the this command is a spark.read.format, and I'm reading the delta format, and .load is from the location we have the data in, and we are specifying the where condition and specifying the partition that we just created this variable over here, and we are saying repartition to this variable num files per partition, which is 16 in this case, and then we are writing that data and saying data change is equal to false. So data change is kind of a parameter when we are specifying, it's indicating Delta Lake that this compaction is not actual data change. It's just that a kind of operation to optimize the performance, but it's not actual data change. So every time when you are making the data change, it's actually will be data change equal to true, but in this case we are simply coalescing the files, it's going to be false, and then we are writing the data as delta and we are saying overwrite, and then again the same partition that we specified over here will be the options, and we are saving those files. And while it's executing, this is one way to kind of coalesce the file. This works fine, and this is the kind of a standard process as of now, and it's available as part of the open source Delta Lake feature. But Synapse has a different way of kind of achieving the same thing, and I'm going to go into more details about that new and different way of kind of optimizing the performance or optimizing the structure of the files in my second video. So at this time, if you can see, the command has executed successfully, and if we go back to a storage location one more time and refresh this page, what you see here is we have like 16 new files which have been added over here, because we kind of wrote those 16 files but after coalescing, and those old files is still existing into this location. So 200 old files and new 16 files which have been created after coalescing. So if you kind of do a sorting on say blob size, let me kind of do that. In descending order, you see this, all these 16 files are almost like 26 to 27 MB in size, and rest other. This is my most recent active record or data files which has the kind of data compacted into this smaller number of larger files, and then the old data exists here in those smaller files. Right, so this is how we can compact the data. This comes very handy, especially in the case of streaming, where you keep on writing the data as it arrives, and those files getting created are very small in size. Right, so this is file compaction, and this is another cool feature of Delta Lake. Now we looked at how we can convert Parquet file to Delta Lake format. Which you'll often find in a scenario when you are working with Apache Spark, because that is a new way of working. That's one of the latest innovation in Spark community. That's something that you're doing very often, but there will be a very rare situation where you need to kind of convert your Delta table to Parquet file. And I would say rare in the sense that I have not seen any situation where I had to convert from a Delta Lake table to Parquet table. So if you have that requirement, what you can do is you can run, as we know that a Delta Lake contains the active data and all the history of changes that has happened into that table. So what we have to do is basically we have to keep only active data in the table and remove all the history from that table. So that's the first thing that we have to do, and to do that we need to kind of run the vacuum command by saying 0 as a parameter. So in this case we are saying anything like other than the recent version should be deleted from the table. And when we execute this command will fail, and let me kind of execute this and show you why it fails. So as we were expecting, this command has failed, and this is because there is a configuration called spark.databricks.delta.retention duration check.enabled, and this is set to false. So there is a kind of check already kind of enabled into a Spark to ensure that you do not accidentally delete the data which are in progress or which are being kind of accessed or updated by a different process in parallel. So if you have any data which is kind of say from the last hour or from last day, and then there is another process which is kind of accessing that data, and if you try to delete that data, you might corrupt the data, and that's where the default duration for retention of this historical data is 6 to 160 hours, or basically 7 days, right? So when you run the vacuum command, it's going to run it's going to delete the data or files anything older than 7 days, which was changed 7 days before. So it's very unlikely that any data which was changed in 7 days will be kind of still being updated by another process in parallel. So it 7 days window seems to be a good fit here. So that's a default set over here. If we want to delete any data within that 7 days window, we have to first go back and change this configuration to false, right? So currently it's set to true, right? And we have to set it to false, right? To do that, let me kind of clear this text from here, and we can look at this configuration. If we execute this command, it's going to give us a value true, which indicates that feature is kind of enabled. We first have to kind of disable this feature. So let me go ahead and disable this feature. And now if I come here and look at the configuration value, it's changed to false. Now if I go ahead and execute this command, so what's going to happen? Any data, let me first execute this command. So now the command has executed successfully, and if we go back to the data lake storage again one more time and look at the data for this specific table, and as if you remember, right, so we deleted the data for January, right? So in my active table or active state of the data doesn't contain data for January. So if you go to this folder, you see there is no data here in this folder. Likewise, you can go and validate the data in other folder as well, and it will only contain the data which is kind of active. The older data, anything older than that, will be kind of deleted. So as you can see in this case, for month of March, we had 200 files, smaller files, and we kind of coalesce those files to create 16 larger files. So we had this older 200 files as well as 16 newer files as well. So we had those changes kind of stored here in Delta Lake, but because we kind of vacuum everything and kept only the active data, those 200 files have gone now, right? So basically, if we go back and look at the data, it's going to give us the data for February and March, but the March data is coming from the kind of compacted files. It's the same set of data. It's going to give you the same value, but it's coming from the compacted file instead of those large number of small files. So this is how you can kind of first run a vacuum command on the Delta Lake table, and then let's go back here, and once you have done that, you need to delete the Delta log folder that gets created as part of the Delta table, right? So first you have to run the vacuum command with 0 parameter to kind of remove all the historical changes or all the version and keep only the active record, and then delete the Delta log. When you kind of execute the vacuum command, and if the parameter is for anything less than 7 days, it will not allow you to do that because of the configuration check that has been enabled by default. You have to check, you have to kind of change that retention duration check property to false before you kind of start running that command, right? So this is how you can convert Delta table to Parquet table. Again, as I said earlier, in my experience so far, I have not come to a situation where someone has to kind of move away from Delta Lake to Parquet format, but know that if there is a need, there is a way to do it. So with that, we are end of this presentation and demonstration of how Delta Lakes work. In part 2 of this demo, I'm going to talk in more detail about best practices and continue on some of the guidelines that we discussed today, and build on top of that and talk about more to get the superior performance. At this point in time, because we are done with our demonstration, you can come here on the top right corner, and you see there is an icon to kind of stop the session. So when you click on this, it's going to ask whether I want to stop this session, and when I say stop now, it's going to stop the session and underlying cluster, shut down the underlying cluster. So at this point of time, my resources of the cluster will be released, and I'll stop paying for those resources. So this is where you can kind of stop your resources that you are using. Now to clean up the data that you have created as part of this demo, you can go back to Storage Explorer and can go to say folder where you created this data, and I created this data as Delta demo. I can go ahead, right click and set delete. It's going to delete all the data that I created. Although the storage cost is very minimal, but if you want to clean up everything, you can click here and remove all the data, and you'll stop paying for the storage that we created as part of this demo. With that, it's time to say goodbye again for now. In my next video, Delta Lake Part 2, I'm going to talk in detail about best practices and how to optimize it for superior performance. Thank you once again for watching. Please do like, subscribe, and let me know your feedback or any specific topic you'd like me to cover next. Looking forward to see you all in the next video.